All right, so I think it's time to start. Thanks everyone for joining Andrey's lecture. So this is great pleasure for me to introduce Andrey Kupavskii, who is vice head of our lab and the young great specialist in combinatorics. And today Andrey will give a talk about random restrictions and forbidden intersections. Andrey, please.
Thanks a lot, Maxim, for this introduction. Yeah, it's a little bit particular to give a talk on this seminar, since I'm one of the organizers as well. But yeah, eventually I gave in. Maxim suggested for me to do this for a while, and eventually I gave in, and I'm doing this. I hope that it wouldn't be the worst talk of the lecture series. I'm personally really excited about the results, and I hope that you'll find them interesting as well. It's very much work in progress, and at some point Dima Zakharov joined it, and we are kind of still going through some of the possible applications of the approach that we found. Yeah, actually, I hear a slight echo. Do you as well?
No, everything is fine.
Everything is fine. Perfect. Okay, then it should be fine for me. So let me start with random restrictions. This and just some definitions and so on. So the random restrictions part was super important, and was a very important innovation that several people that I'll talk about, Alweiss, Wu and Zhanga, came up with in the context of the Erdos-Rado sunflower problem, and I'll talk a little bit about this sunflower problem. But it turns out to be applicable to some other problems, and that's in particular the forbidden intersection problems. And for that to kind of formalize all that, I'll need some definitions. So I'll use this n square brackets for the first n integers, positive integers. 2 to the power set would be the power set of 2 to the power x would be the power set of x, and x choose k would be all the set of all k element subsets of x. I'll use also x choose at most k, which you can guess what it means. We'll be working with families, so a family is simply a subset of 2 to the n. And one thing that one piece of notation that we need as well is this: for a family f and a set x, we'll use this notation a minus x. We'll use this notation f of x, which is all sets from f that contain x, and with x removed. Okay, so the key definition for this talk is the R spread definition, I guess. And we will say that the family is R spread if for some positive number R, if roughly speaking, when no set or no subset of the ground set is contained in too many sets of F. So formally, if we take any set X, a subset of the ground set, then the cardinality of this f of X is at most R to the minus the cardinality of X times F. So we have this kind of exponential decay depending on the size of F and the size of X. Yeah, so this is the notion that would be very important. But we'll need another thing. We'll need this kind of a shortcut notation. We'll say that W is a p-random subset of X if each element of the ground set X is included in W independently with probability. So we sample for each point we throw a coin with probability P of success, and then we obtain some subset W. Okay, so the main result that gave significant progress in the sunflower conjecture is due to Alweiss, Lovett, Wu, and Zhang. Is here on this slide. We present a version by Terry Tao with some parameters kind of being optimized and made explicit. So the statement, roughly speaking, I mean, there are lots of parameters here and you don't have to read it in details, but the statement says the following: if your family is sufficiently spread, so R spread for sufficiently large R, then you have a good chance of getting a set from your family that belongs to a p-random subset of the ground set. So we have a p-random W in the ground set, and if the families are spread, then there is a good chance that there is a set from the family lying in this W. So it's a little bit technical, this statement. So let's stare at it for a little bit. The kind of key point here, I guess, is that there is this, in this expression for the probability, there is this exponential decay kind of in M, whatever M is. So let's maybe try and kind of figure out what are the parameters that we can plug in here, because we need to familiarize ourselves a little bit with this statement because we'll use it later. So R and K are kind of fixed. So the family have sets of size at most K or exactly K, doesn't matter. R is the spreadness parameter, and then there are N doesn't really participate anywhere, so the ground set at that point is not important. And then there are two parameters that we can choose: M and delta. Essentially, the way it will be applied here and the way it is applied is you make sure that here in this expression you would get 1/2. So basically you make R delta to be 2 to the 10, so some constant. And then the probability of your event would be something like 1 minus 2 to the minus M times K. In which case, in order to make this probability very large, you can take M to be logarithmic in K. delta, you'll take something like P over M, where P would be, that would be the P subset W. So this would be P. And well, our delta is 2 to the 10. So essentially, R that you need in order to make any use of this statement is logarithmic in K times or divided by P that you would need. Yeah, and so yeah, this is the statement. And deduce from here. So it's actually, it's very powerful. One thing that one can deduce is the existence of large sunflowers in the family. What is a sunflower? A sunflower is simply a collection of T, well, a T sunflower is a collection of T sets such that the intersection of any two of them, well, different two of them, is equal to the intersection of all of them. So in particular, matching, so this collection of pairwise disjoint sets is a sunflower, but yeah, in general, need not be matching. So why is it the sunflower? So you have this common intersection. It's called the sunflower. You have this common intersection, and then you have these petals that correspond to sets minus the common intersection. Great. It is, from the statement above, it is not difficult to deduce the following corollary. It states that if your family is sufficiently R spread, then well, where sufficiently is essentially constant T log Tk. So constant T log K, if you think of, or if T is constant, then it's just constant log K. Then your family is guaranteed to have a T sunflower. So actually, even for T equals 3, this problem is very hard, and we don't know the like we don't know anything better really for T equals 3 than for general T. So T being a constant is a totally valid kind of setup. And so how do we get it from above? So the parameters are such, well, I wouldn't have delta to be 1 over T. T is the size of our sunflower. This to be 1 over T, and this probability would be something like 1 minus 1 over 2T, at least. So the proof, or a sketch of a proof, is as follows. So apply the theorem and get that the conclusions again that the probability is bigger than 1 minus 1 over 2T, the probability above, for a 1 over T random W. So these are some calculations that I'm not verifying, but I read the constants explicitly here just to make a point that they're not so bad and that they can be made explicit. But yeah, so trust me on this. So this is 1 over T, and this probability would be 1 minus 1 over 2T, say. And then what do? We just take a random coloring of N into T colors. well, each color is a 1/t random subset. Since, of course, each element is included in a particular color with probability 1/t. And then we just apply union bound. For one such set, we have probability 1 minus 1/2t of containing a set lying entirely in that color. So using union bound with probability at least 1/2, there would be sets lying in each color entirely. And in particular, they form a matching of size t, so a sunflower of size t. Union bound, get a set in each color. Get a set in each color, and this is a matching. And thus a sunflower. This is a T matching, thus a T sunflower. Great. Yeah, now it's much better. Great. So is the proof clear that I presented? Yes. Any questions? Okay, good. And then the second corollary is it states that if your family is sufficiently large, where large, well, the number written here, the number written here is precisely the spreadness of the family, and then we take it to the power k. So if your family is sufficiently large, then it contains a T sunflower. So to prove this corollary, it amounts to show that we have a subfamily that would of F somehow that would be that spread. So let's denote this thing by Q, and then the proof would be find maximal x such that f of x is strictly bigger than q to the minus cardinality of x times the cardinality of f. If f is q spread, then we're done by previous corollary. So assume that not and find maximal x such that this x violates this property. Or if we want, we can. Yeah, the strict or non-strict inequality doesn't really matter. And then f of x is q spread by maximality, and that's it. That's the whole argument. And the condition that we write on the cardinality of f here guarantees that we cannot take x to be a set of size k, because then the spreadness property is vacuous. Of course, we cannot deduce anything if we go up to size k. But the conditions on the cardinality of f and this inequality guarantees that this would hold for some x of size smaller than k. And then f of x is q spread, and actually contains some sets, and we can apply the previous corollary to get a, so we can apply this to get a sunflower. So that's how it works. So the main thing in Alweiss and others' paper, of course, is this statement: the possibility of finding a set in a p-random inside a p-random subset of the ground set if your family is spread. And then it's simple to reduce the sunflower problem to that. So before the just to mention, so here we have this bound where let's think of t being constant. The bound is like constant log k to the power k. The previously best bound, well, more or less best bound was due to Erdos-Rado, who asked the question of improving this, and it was k factorial t to the k. So k to the k instead of log k to the k. Yeah, and the proof actually bears some similarities with the proof that I told you now, in a sense that they've used some very rudimentary kind of properties of spreadness. So what they would do is they would say, if you don't have a sunflower, then the largest matching that you can have in the family has size t minus 1. So this is your matching of size t minus 1. So in total, k times t minus 1 elements. And this matching must intersect, well, every set from F must intersect this matching somewhere. And thus, there is X such that, well, from this matching, such that F element from the ground set, which belongs to this matching, such that F of X has cardinality, at least the cardinality of F divided by K times T minus 1. And then you apply induction because you've reduced uniformity by 1. And you see that this thing is kind of, we are violating spreadness for step 1. So if the family was that spread or bigger than that spread, then there is no such X. So yeah, there is some at least superficial analogy. Okay, so that was a detour to sunflowers, and I hope we get ourselves a little bit familiarized with the spreadness and with this statement. So now let's get to the topic of the lecture, main kind of to the results in the lecture. So I'll start with intersecting families. We say that the family is intersecting if, well, any two sets in the family intersect. Yeah, from now on, I will mostly work with uniform families. So sets of size exactly k. And for uniform families, there is this Erdos-Rado theorem, which states that the largest intersecting family you have is what is called the star, all sets containing a fixed element. So in particular, the size of F is at most n-1, choose k-1. And then there is a whole line of research, lots and lots of papers that studied kind of stability of this Erdos-Rado theorem, which means the following: how far so how kind of far can a family be from this trivial intersecting family if it's sufficiently large, if it's close in size to the trivial family. So that's the rough spirit. So, or maybe I should formulate it a little bit differently. If the family is somewhat large, the intersecting family is somewhat large, can we find a structure in this family that is in some ways resembling this trivial intersecting family? And there are many results here, as I said. So first result was due to Hilton and Milner, who proved an upper bound non-trivial intersecting families, so not all sets containing a fixed element, a good bound for n sufficiently large as compared to K. And there were many other results by Frankel and myself and Dima Zakharov also wrote something, and many papers, kind of getting different type of stability or different type of structural results. So there are kind of three avenues to get this stability results. The first one is specific for intersecting families. Hilton-Milner result is very much specific for intersecting families. That's a tight stability result. It's very rare that we can get tight stability results. For intersecting families, we're lucky because we say have somehow Kruskal-Katana theorem at our disposal and some other tools. We can shift families, and shifting preserves this intersection property. That's also a super strong property. So there are some specific things for intersecting families or shifted families. For shifted families, we had a very tight kind of approximation result with Peter Frankel several years ago. And then there are two general methods that apply for a much broader, actually, class of problems than just intersecting, like kind of finding structure in intersecting families. First one is the sunflower or the delta system method. And it was developed by Peter Frankel and then Frankel and Furedi and Zoltan Furedi, and then well, they wrote papers individually, they wrote papers together and solved many problems. The thing is that, well, to be more specific, there are two variants of this delta system method, one variant that we need, say, for many results in intersecting families would imply bounds where n should be at least polynomial. Okay, so something like, imagine something like k to the 9, this kind of bounds. And for harder problems, for example, for the forbidden intersection, one intersection problem that I'll talk about later, it would imply bounds that are exponential, or maybe, no, I probably should say even double exponential, 2 to the k. So there are these two variants. I wouldn't go into details on how the sunflower method works or this approximations method works that I'll talk about now, but but the very rough idea would be somewhat similar to what we will see later, and it is that somehow you can select small subsets, very small subsets of the ground. So sometimes it's just one element or 2 element sets, 3 element sets, and that you claim that most of the sets must contain them. and from the family must contain them, and then you prove some results about this structure of very low uniformity, and you go from there. So you prove something about the structure of this very low uniformity family, and then you say that most of your family kind of looks is contained in this thing, and there is a small defect. And this defect, you can handle it by saying that, well, if you start to change your family a little bit, then then it gets worse. Or if you want a stability result, then you already have your stability result because the defect is small, and you say that all the family should be contained in some very nicely structured thing, which is encoded by this low uniformity sets. So this is essentially a description of this Frankel's, so to say, Frankel's variant of sunflower method. In order to get such a thing, you need to apply sunflower lemma somehow. In order to extract the structure, you need to apply the Erdos-Rado result. And Frankel and the Furedi approach and Frankel and Furedi approach, it also gets a very structured, kind of nicely structured part of your family, but in a different way. Somehow you filter, you get a very, very tiny, tiny in terms of k, but still kind of, if you think of k as a constant, linear proportion of sets that are very, very highly structured. Somehow their intersection patterns are highly structured, and whatever intersection pattern you fix, then you'll have a sunflower. And then when you have this very structured kind of subfamily of your family, then you can do some. Then you can extract things. So that's a very rough description of the sunflower method. And then there is the junta approximation method. So junta approximation method is different. And very roughly speaking, it says that if you have, say, an intersecting family, then you can approximate it well by an intersecting family that depends on few coordinates, on a constantly many coordinates. So let me show you a statement. So first, since it's a bit maybe it's a bit better for comparison because there are general statements, approximation statements using juntas. So we say that a family, first of all, let's define what is a junta. So informally, if you think of a family as a Boolean function, then it's a function, we say that the function is a J junta if it depends on at most J coordinates. So slightly more formally, and in terms of families, we say that the family is a J junta if we can find a subset X of the ground set of size at most J, such that, deciding whether A belongs to J or not depends only A intersection X. So we look at A intersection X, and depending on what intersection we get, we include A or do not include A in the family. So we depend only on coordinates from X. And then there is this the result of Dinur and Friedgut, which is the first junta approximation result, which states the following. So there are some parameters, again, you don't have to read it out, but most importantly, I should change this thing to R. And R here doesn't have to do anything with spreadness, it just happened to be the same letter. So we start with fixing some parameter r, which would be quality of our approximations, and then we find some functions g of r, c of r, such that we have the following. So if we have an intersecting family, then there exists an intersecting J junta, so intersecting family that depends on J coordinates at most, such that most of the family is contained inside this junta. So F minus J has size at most C is this constant C of R, and N minus R choose K minus R. So this is a result that allows us to get some kind of stability of Erdos-Rado in a very kind of large sense for N being linear in K. The only problem with this type of results, with this result and this type of results, is that this dependence of J on R and C on R is unspecified, and it's also well, I'm not sure, but I believe that it's also like doubly exponential. So if we want to get some approximation for some fixed R, then the statement is good, but we cannot really allow R to grow. Then the statement stops working. So in a sense, and one thing I should say is that this thing was this was extended. So this was extended or greatly extended in works of Ellis, Keller, and Lifshitz. I would say that Lifshitz is the driving force probably behind. To a very large class of Turan type problems, so to say. What do I mean by this? I mean that we have similar results for many other questions, instead of a family being intersecting, we can forbid some other configurations, for example, sets intersecting in exactly T elements, so that's what I'll talk about later, or the triple of sets that would have some kind of intersection. But the moral of the story that both, for this part of the story, is that both this delta system method and junta approximations work for general Turan type problems. And the kind of advancement of this junta approximation is that before we had the condition that n should be bigger than n0 of k, and now we have a condition that n should be bigger than n0 of t, where somehow t is some kind of complexity of the problem. So, for example, or complexity of the problem, quality of approximation. So all of these things go into T. So K, the uniformity doesn't go there. But for example, T, if we want to approximate families with one forbidden intersection, then T is this intersection. So this parameter, this complexity, would be the size of the intersection that we forbid. And if you have a bunch of sets, then you should count the number of elements that are contained in at least two sets. For example, this can be a notion of complexity. And then, yeah, so you get this, you get similar type results for general to run problems, provided that n is sufficiently large as compared to t. Again, not, let's say, unspecified function. So we always think of t as being fixed. So no one made effort in this context of junta approximations to actually specify how this dependence goes, but it's clear that it's very bad. Yeah, and then what would be the strategy of, yeah, so I should say that junta approximations do not just give you an approximation, that they actually help to solve many problems and in different regimes. And how would the typical proof go? You start with a family obeying a certain restriction, intersecting, t-intersecting, something like that. Then you find an approximating junta that is also t-intersecting or intersecting. You prove something about the structure of this junta. So this, on this small set of coordinates, you have this small family on this small set of coordinates, and you prove something about the structure. And it's easier because this family is this kind of part of the ground set is of constant size, and then it's somehow much easier to prove things about it. So you get some kind of the best possible junta for your particular problem. And then you say that if your family is extremal, then it must be approximated by the best possible junta. And thus, you're only left to deal with the remainder. The sets that did not were not captured by junta. So here we had this remainder in the statement. So you only have to deal with this part of the family, f minus j. And typically you would say that, well, small perturbations of this junta cannot lead to increasing the size. So that's how it works, and it's similar in spirit to what Frankel did in his work, and also to what Frankel and Furedi did to some extent. Although it's maybe a little bit well, the general spirit is like that. You find some structure, you prove that some not so complicated structure, you prove that it should be, in order to be optimal, it should be something, and then you say that what you had was close to it, and then you say that it should coincide with it. So our result about intersecting families, or in general, is also similar in spirit, but it gives but it's still quite different from junta approximations. It also can be applied in general scenarios, but yeah, it's different from junta approximations in many ways. So let me specify. So we fix some parameters, and here I guess the main thing to note is that we require n to be at least k log k, which is probably the only big kind of drawback, that we cannot take k to be linear. Then we start with an intersecting family, and we say that for this intersecting family, we can find an intersecting family of sets of size at most q, and the remainder f prime, such that the following things hold. Well, first of all, well, the property 1 and 3, it should be at the end, are saying that essentially most of the family is kind of contained in S. So the first ones is just a little bit more tricky to say in this case, because the families are of different uniformity. But what we say is that for all sets in F minus this remainder F prime, there exists a set B in the this family S, such that B is contained in A. So, in other words, if we extend S in all possible ways to sets of size K, then it will cover all sets in F minus F prime. The third property says that the remainder is small. And the second property gives us some kind of quasi-random properties for sets from this family S, from this approximating family S. For juntas, actually, you can also get some kind of quasi-random properties, but in very different terms. So here, this quasi-randomness is expressed in terms of this R spreadness. So you can think of R spreadness as being some kind of quasi-random property. It says that for every B in your approximation S, you can find a subfamily in F such that this F, some family FB, such that FB of B is, I don't have R here. I think it should be something like N over 2K spread in this particular statement. I mean, it's a little bit of a pain because, again, there are many parameters, because in this Alweiss and others statement, we had also many parameters, and the statements are very much related. But yeah, let's digest it a little bit. So the main drawback, as I said, is that N is required to be bigger than K log K, but in many cases, it's not such a big deal because you worry about larger N. A big advantage is that you have a very, very explicit quality of approximation. So before we had some constants, some very, very like unspecified dependencies, and we really could also only get this junta approximations for R fixed. So something like, polynomial quality approximations, K divided by N to the power R. And if you think of this, K divided by N is, well, if N grows, then it's some function of N. So this function of N to the power R. Here you get exponential type approximations. 2 to the power minus Q, where Q lives here in this statement. So if N is bigger than Q times K, then you get here 2 to the power minus Q quality of approximation. Then yeah, of course, these approximations are different, and in some sense, this S, the way it looks like, it's closer to this first what I would explain, the sunflower method by Frankel and Furedi, because we're not approximating the family on few coordinates, but we are approximating the family on using sets of small uniformity. So this is the statement, and to demonstrate its strength, let me derive one corollary. So actually, Erdos-Narayanan was asking me about it, and the question was as follows: what can be said about the size of regular intersecting families? So we say that the family is regular if, well, each element has the same degree. So in the notions that we had, cardinality of f of x is equal to f cardinality of f of y for every x and y from the ground set. And the corollary that we get is from the statement above, is that as n grows, the size of this regular intersecting families decays exponentially. So you see the bound on their size 2 to the minus q times n choose k, and q is essentially n divided by k. So let's prove this just to see how the proof goes. Proof. So if well, assume that the cardinality of f is bigger than this 2 to the minus k, choose k. Take approximation as above. So the one guaranteed in this statement. I mean, I chose the parameters so that these conditions are satisfied, so we don't need to worry about that. And we get this family S of sets of size at most q. And first thing to note is that because of this condition that I wrote here, and this condition, we see that, well, the cardinality of f prime is at most 1/2 the cardinality of f. And all sets in f minus f prime intersect any set in S. Let's think about that. So we have this approximation S above, and I'm claiming that any set from this f minus, from here, f minus f prime, intersects any set from here. So let's fix one set B. We know that any set from here, any set A from here, contains some B prime from S. And we know that S is intersecting itself, so B and B prime intersect. It means that A from here and B intersect. So in particular, this implies that for say B in S, there exists.
Yeah, so can you repeat the last argument? As far as I see, you have said in S, you have a set that is contained in.
Yes, so we have a set in S that is contained in any set from f minus f prime. And then any two sets in S intersect.
Right.
So it means that you have a bigger set, then you have a smaller portion, and this smaller portion intersects this B. So the bigger thing also intersects this B.
Yeah, now I see.
So from here, we deduce that for B in S, there exists some element X in B, such that the cardinality of this, let's say, f of X, all sets containing this X, is at least 1 over the size of B times the cardinality of f minus f prime. So any set from f minus f prime intersects B. So just take the most popular element X from B that is intersected by the most. It will cover 1 over B proportion of all intersections, all sets. So, and this thing is at least 1 over 2Q times the cardinality of F. I use this bound. So since F prime is at most 1/2 of F, this thing is at least 1/2 of F. So this is where we get this 2. And I just used the fact that any set in S has cardinality at most Q. That's how I get this bound. And this is a contradiction with regularity. Thus, F is not regular because in regular, cardinality of F of X is equal to K divided by N times cardinality of F, just by double counting. Each set contributes to K elements, and we have N elements in the ground set, thus the degree of each element should be K over N. And K over N, in our case, is equal to 1 over 4Q, cardinality of F. So that's a contradiction. So very, very easy deduction, but so somehow it was absolutely unclear how to get this kind of results before. And essentially the same bound before was known for symmetric intersecting families. So when you assume that there is a transitive group of symmetry acting on this family, and this was due to Ellis, Kalai, and Narayanan. I say here a similar one because they could actually get something for N being linear in K. But for N, say, being K to the power 3/2 or K to the power 1 plus epsilon, the bounds that we get coincide. And actually, the bound that I told you is better because the constants are explicit. They have exactly the same bound, but with unspecified constants. Say 2 to the minus Q, it would be some C to the minus Q. C is something bigger than 1. And for regular intersecting families, I wrote a paper with Iringer, Ferdinand Iringer, before, and we could only prove a polynomial decay. We used juntas, and this thing says that we can get, roughly speaking, polynomial is small for polynomial of any degree. So for any fixed R, most n minus R choose K minus R. Yeah. Okay. So that's for the intersecting families. But
yeah. What about sharpness of this result?
It's a good question. I haven't checked, but I should check it. I think that it's not far from being sharp. I need to see what kind of constructions we had with Ferdinand, but I think that it's not so far from being sharp. Unfortunately, I don't remember now. One thing to add to this problem is that these regular intersecting families only exist for specific parameters. You cannot take n too large. So n is at most k squared, roughly speaking. The extremal example, kind of for n being the largest, is a projective plane, finite projective plane of order q, order k. So n is at most k squared. And well, if you substitute k here instead of q, the bound wouldn't be so bad, right? So it's 2 to the minus k times k to the k, roughly speaking. So of course, we want to get, well, 0, more or less, but the bound would give you 2 to the minus k times k to the power k, so it's not so bad. And we had some constructions that somehow started with a smaller projective plane and then extended it to everything, but I don't remember what it gives here. But the extremal setting shows that the result is actually not bad. not so far from being correct. So the method that we have extends to a larger class of problems, much larger than just intersecting families. The nicest applications are to Erdos-Sos type problems. So what is an Erdos-Sos type problem? We ask for the largest family without a fixed intersection. So we say we forbid intersection t minus 1, no two sets intersecting t minus 1 elements. How large can a family be? And if n is large compared to k and t, somewhat large, the natural example would be something like sets from n choose k that contain first t elements. So in order to guarantee that we do not intersect in exactly t minus 1, we just make the family, so to say, t intersecting. So all intersections are of size at least t. That's a natural example. And let me summarize previous results. So Frankel and Furedi proved it for t is smaller than k over 2. This is necessary to impose, and n being large. So this is the sunflower method. This condition t smaller than k over 2 you needed, because if t is bigger than k over 2, then instead of having this, instead of saying that all families intersect in many points, it's more interesting to make design type constructions, which would give you or code type constructions, which would be like no two sets intersect in too many elements. So before we had no two sets intersecting too few elements. For bigger t, you would have many elements. And the problem is actually harder for t bigger than k over 2. Frankel and Furedi also gave some very good results in that regime. And it's related to existence of designs and these kind of things. Then, if you ask for the t intersection property, so instead of forbidding intersection t minus 1, forbidding all intersections from 0 and t minus 1, for a long while it was an open problem, also studied by Frankel and Furedi, and finally solved by Alweiss and Khachaturian, who found the exact answer for all n, t, and k. And in some regime, of course, again, this family A is the best, but there are families of the form AI, so all f from n choose k, such that f intersection t plus 2I has size at least t plus I. So again, you can see that it's t intersecting, and for some regime, this is better. Then recently, by this group of authors I said, Lifshitz and others, they, using junta method, they solved essentially the Erdos-Sos problem for fixed t, and n and k being large and as functions of t. So for fixed t, the problem is essentially solved. Also, they got some nice stability results for both Erdos and Sos and Alweiss and Khachaturian, using junta method. Hard proofs, and all this actually, or most of these junta type proofs are hard and technical. Using Boolean analysis, some results about coming from Boolean analysis of Fourier transform, and quite a lot of machinery you need, quite a lot of details. So the bottom line of all this is that no one knew how to deal with growing t. T couldn't grow, and one of the things that we can get is make t grow. So let's first, well, yeah, it's a long statement, unfortunately, but it's similar to the previous statement. So before we go into details, the intersection proof, the proof for the intersecting families, is relatively simple, and I'll sketch it to you, hopefully, if I have time at the end. Actually, it's really short. It's one page, one and a half page proof, maybe. In case when you want to deal with this Erdos-Sos problem, you need extra tricks. Somehow it gets harder, and one key idea is to use spread families that are very, very spread as possible, almost. And for that, I introduced this notion of tau homogeneous. So tau homogeneous is an analogous notion to spreadness, and it goes as follows. So we say that the family is tau homogeneous if for every A of size small a, the cardinality of this f of A is at most tau to the power A times this ratio of binomial coefficients times the cardinality of F. So how to parse this? So one thing to note is that if we put tau equals 1, then what is written on the right side, this thing, n minus a choose k minus a divided by n choose k times the cardinality of F, it's the average size of f of a for f of big A, where a is of size small a. So that would be, this would be just an average value of that. So, and we cannot guarantee, of course, this kind of spreadness or this kind of homogeneous. So one homogeneous is impossible. It's possible only for the family of all sets. So the only family that fits this definition is the family of all k-element sets. Tau is the, so this tau homogeneous, now maybe it is clearer. You should think of tau as being very close to 1, and thus you see that family is extremely regular. So if tau is small, then almost all the sets have almost, the same number of elements, so almost all the sets A have almost the same sizes of this f of A. So that's the idea behind this definition. Extremely regular kind of situation. And so with this notion in mind, yeah, well, I'll comment on this later. It's actually strange that we use such a, for me it was strange to use such a strong thing, but somehow there is, we can afford it using this approach. And then the statement says roughly as follows. So there are some parameters, and we start with a family that has no two sets intersecting in t-1, exactly t-1 elements. And then we can approximate it by a t-intersecting family of small sets, such that, and then the properties are roughly the same as before. So property 1 and property 3, it should be again 3, says that almost every set is contained in S, or for almost every set, there is one of its subsets comes from S. And the second property says that something very similar again. So for every B in S, there is a subfamily of F such that FB of B is tau homogeneous for some very small tau. So very similar statement to what we had before. The R spreadness replaced by this tau homogeneity, and the parameters are a little bit worse. So to make this work, Q now it has this form, this t squared log n over k. So Q is somehow bigger than what we had before. If you look at what we had before, then what we could write here is, well, 2 to the minus q directly. Q transformed to this 2 to the minus q bound. Here, if you look at this statement, we have this k over n to the power 10t. So 2 to the power k 10t log n over k. But q is not t log n over k, but t squared log n over k. And this t squared comes from the fact that we want to be very homogeneous. But still, all the parameters nicely interdependent. Nicely in the sense that dependencies are explicit polynomial or low degree polynomial. And nice feature is that we start with this family avoiding one intersection and we approximate it by a t intersecting junta or random restriction kind of approximation. A corollary of this thing is that we can solve Erdos-Sos for polynomial values of parameters. I stated slightly informally, but basically, if n is equal to k to the power alpha, t is at most k to the power beta, and the parameter is nkt is before, of course, so k element subset of t element set. No intersection t or t minus 1 doesn't matter. one forbidden intersection. So then, provided this inequality holds, alpha bigger than 1 plus 2 beta, and k is sufficiently large, then we know that this family A from above is indeed, this family A is indeed extremal. So solution of Erdos-Sos for polynomial values of parameters. That's really nice. Because before we didn't know how to make t grow, and now we know how to make it grow polynomially with some nice dependencies, not too bad dependencies. So for example, we could take n to be k squared and t to be, well, square root of k, for example, and it would be fine. Probably I should also state somewhere that beta is at most 1/2. Or strictly smaller than 1/2, and that we need also. I forgot to put this. So we cannot make t to be k over 2, but we can make t to be roughly a root of k. One feature to note is that actually that would be important for the next thing that I'll say, is that, well, we get in this statement, we get this bound on the size of the remainder, but actually the way we get it allows for more. So the way we get it is that we can compare the size of the remainder with the size of some f of s, so your family sets from the family containing some fixed set s, where s has size bigger than q. So you have a direct comparison. Well, it doesn't matter this coefficient, but imagine that it's good. But you have a direct comparison between the size of this remainder and the size of sets containing sets from your family containing a fixed s of large size bigger than q. And the next application I find probably to be the most exciting. First of all, the parameters would be very clear, and second, people really struggled to get anything about this type of problems before. And we get some really nice results using the approach that I just kind of talk about, and it's not a difficult approach. It would be about intersecting families of permutations. So we have permutations from n to n, family P of permutations from n to n. We say that it's intersecting if for every 2 permutations from your family, they map one element x to the same place. And analogously, you can define T intersecting, you can define intersecting in exactly T points and so on. So all these kind of properties that we saw for families of sets can be transformed to families of permutations. And Deza and Frankel asked, what is the largest T intersecting family of permutations from n to n? So it's easy to get actually that one intersecting, it's at most n-1 factorial. Well, of course, total number of permutations n factorial, and for one intersecting, get n-1 factorial. It's really an easy proof. You can just decompose a set of permutations into n tuples of permutations, such that in each tuple, the permutations are disjoint. So you can take at most one from each tuple. Easier than the Erdos-Rado statement even. Doesn't even require double counting. But then problems started. You could not, for a while, you couldn't even prove that this there is some kind of uniqueness as in the Erdos-Rado. Notably, that all the kind of families of this one intersecting families of this size are essentially families that fix one element, to map one element to the same place. So for example, if you map 1 to 1, then of course the number of permutations in the n-1 factorial, but and there are analogous families that map A to B all. And it was hard and to get that only these configurations are extremal. So Cameron and Ku and independently Larose and Malvenuto did this. Then there was a very hard paper by Ellis, Friedgut, and Pilpel that solved the T intersecting problem for n bigger than n0 of T. 50 pages paper, and it uses Fourier analysis, it uses representations of symmetric groups, so algebra, representation theory, and generally hard. And then there was a recent paper by Ellis and Lifshitz, who managed even to get Erdos-Sos for n bigger than n0 of T. So again, for fixed T, you can get that what's the statement is if your family of permutations avoids intersection T-1, then the size is at most n minus T factorial. So no intersection T-1, thus size at most n minus T factorial. Also, similar techniques in a way, plus some extra things. So again, Boolean analysis, representation theory, Fourier analysis, representation theory, this kind of things. And yeah, so together with Dima, we can solve this problem, both the T intersecting and the Erdos-Sos for T smaller than square root of n, roughly speaking, minus some little of 1. So imagine that n is sufficiently large, and you take any T that is smaller than square root of n minus epsilon, n to the power 1/2 minus epsilon, then if your family of permutations satisfies that there is no intersection of size T-1, then the largest thing you can take has size at most n minus t factorial. And it can be done without any algebra, using this, so to say, elementary approach, just by first kind of remarking the following thing, that any permutation can be thought of as a set. So first you can represent a permutation as a matrix. So permutation matrix. So for example, this permutation is 1, 2, 3, 3, 1, 2, then the matrix would be, so let's say that these are elements, this is n, and this is sigma of n. I'm not sure what's the standard way of writing, but then it would be 0, 0, 1. So meaning that 1 is mapped to 3, so there is a 1 in the third column, then 1, 0, 0, 0, 1, 0. So that would be your matrix. So permutation would correspond to a permutation matrix, and then you can think of it as a set. So this is just something that belongs to n squared, choose n. Before, with these junta-type methods, you couldn't work with these kind of things because, of course, the number of permutations is much, much, much smaller than this n squared choose n. But and even our method doesn't seem to apply because, okay, we have this exponential decay, but it's not enough. But one thing to note is that actually, as I said, we get a comparison here between a family, a size of the family, and the size of the remainder, and all sets from your family that contain a fixed subset S. And then you have a kind of bound on the remainder in these terms. And this thing for permutations we can control. In particular, if S, the set, has size L, then for permutations, this cardinality of f of S is at most n minus, well, cardinality of S factorial. So we have a control on the right-hand side, and it turns out that the bounds are good enough in this situation to just think of permutations as sets and apply this machinery. And then we need some, of course, extra arguments to kind of so we get this approximation very, very quickly. You need to kind of figure out what does this mean exactly. This what is some kind of partial permutations as, but kind of the other arguments are not so. They're kind of in the spirit of things that appeared in the literature for so to say the sunflower first easy sunflower method of Frankel, delta system method. And you can, so you get your, basically you get your approximation using this result for permutations, or something similar for permutations. You have control over the remainder because of this statement. Yes, that you control this f of S. And then you have this family S of these partial permutations. You somehow manage to prove that the best way for it to be is just consisting of one partial permutation that fixes T elements, because this is T intersecting. And yeah, you can somehow argue about this partial permutations. Since Q is small, you can do things. This the best thing to do is for it to be just one T element set. So your family is already very close to the suggested extremal. And then there is a last kind of bit of argument which says that if there is any permutation that does not contain this fixed T elements, doesn't map them to the same place, then your family is much smaller. So following this exact framework that I was talking about, you can do this. Okay, so that was pretty surprising for me, this thing. But maybe, so how much time do I have, Maxime? 10 minutes?
Andrey?
Yeah. So
Yeah,
how much?
Now it's 8:35. I think that you have like 10 minutes.
Okay, so let's say that, okay, 10 minutes would be enough to at least give you a good overview of what is done here. So the last thing that I want to do, and somehow I did manage my time so well, but still, the last thing I wanted to do is to sketch you the proof of this theorem. So how do we get these approximations using random restrictions? After all, we've seen that
this one or the next one.
No, this for the intersecting families, the simplest one.
Okay.
The ideas behind, I mean, the second one builds up on the ideas here, and the basic idea is very simple here. So so how do you prove it? Well, we'll fix R, this spreadness parameter, to be n over 2k. I don't know if I even would get to some kind of calculations, but anyway, so let's do that. And the first thing to note is that f itself is not R spread. The family is not R spread because it's intersecting. If your family is R spread, we've seen in the beginning with the sunflowers that what you would do is you just randomly to color your ground set, and with good probability in each part, in each color, you will have a set. So these two sets will be disjoint. So your F is not R spread. So thus you can take a maximal S1 that violates this R spreadness condition, meaning
this is a subset in F.
Maximal, it's a subset in the ground set. Sorry, meaning f of S1 has cardinality bigger than this R to the minus cardinality of S1 times the cardinality of F. So now we know that the family is not R spread. Thus, there must be some S1 that violates it. Then there are two scenarios. If S1 has cardinality bigger than Q, then then F is small. Why? Let's see this thing. Because the cardinality of F would be at most this n over 2k to the power cardinality of S1 times cardinality of F of S1. So this thing we can replace by n minus S1 cardinality of S1, choose k minus cardinality of S1. That's definitely an upper bound on the size of this thing. And this thing we can replace by this thing is at most k divided by n to the power S1 and choose k. So that we can do, right? That's just simple calculations. N minus cardinality of S1, K minus cardinality of S1 bounded by this. And thus we get this thing. We get 2 to the minus cardinality of S1 and choose K. Simply. That's exactly the bound we wrote here. Just the last thing to note is that since S is bigger than Q, this is 2 to the minus Q minus 1 and choose K. So that shows that F is small. But if this holds. But then if not, include this S1 into what at this moment empty family S. Now it will contain S1. Put F1 to be F minus F of S1. So just remove the sets that you already kind of approximated by S1 from the family and repeat. Repeat the same procedure. And that's it. That's the whole construction. Let's see what we can get. Well, at some point, basically, once this S1 will be bigger than Q, you just stop and you declare if Si at the step I is bigger than Q, stop, put F prime to be Fi. So just put everything that was at that step into the remainder. Then looking at the statement, we definitely have this. We have this. It's also not difficult to see that we have this. Well, this is R, this R spreadness. For each B in S, we have this subfamily FB, such that FB of B is R spread. So in this situation, for example, with this S1, it would be just simply this family F of S1. So at the later stages, this family FB would be just Fi, simply Fi. So, you know, we modify our family by removing sets. And then this Fi would be the family that we'll use as this FB. And why this Fi is R spread or N over 2K spread? Well, let's see on this example, why F of S1 is R spread? Because we took a maximal set that violates R spreadness condition. So there is no superset of S1 that would violate this condition. And it's easy to see that this implies that F of S1 is itself R spread. We use this trick in the proof of, we use this observation in the proof of in the derivation. When you have a large family, then you have an R spread family. So this thing is R spread because it's S1 is maximal. So this property is also easy. It follows from the choice of B kind of at Si at each step. The only kind of non-trivial thing to check, yeah, and of course all sets in S are of size at most Q, because this is how we construct it. We halt if a set has size bigger than Q. The last thing kind of to figure out is why the family would be intersecting. That's actually also not so difficult to see. So that's the last thing I'll kind of draw. So if you have two sets, well, A and B belonging to your family S, such that A is here, B is here. So you know that for this A and B, you have families FA and FB that are spread. well, FA of A, FB of B that are R spread. So your hope is that what you can do is using this spreadness, you can somehow color the ground set so that you can find essentially, well, two sets such that well, something like that. So this some kind of set X belonging to this FB, and then set Y belonging to FA that are disjoint. So this is your hope. You start with sets A and B that are disjoint, and the hope is to find Y and FA, X and FB that are disjoint. That would violate the intersection property because FA and FB are subfamilies of F. So they must be cross-intersecting. Everything must intersect. But you cannot do it immediately because, well, A and B do not intersect, and sets from here, for example, FB of B may contain elements from A. You don't immediately have control, but it's very easy to get control. So what you replace this family FB of B with the family FB prime, let's say, that would be just the family with the family FB prime. That's the family of sets F minus B such that F belongs to FB. That's the definition of FB of B. But additionally, F intersection A is empty. So you just restrict only to the sets in the family of B that do not intersect A. And apparently, FB prime is almost as spread as FB. That's very easy to see. You just delete an element, you delete a bunch of sets from FB of B, or from FB. You delete a bunch of sets, and you don't delete too much because your family is spread. So elements from A do not cover a big part of FB. So you can delete them, and your spreadness doesn't change that much. And you do the same thing with FA prime. From FA, you start from FA, and then you do this FA prime. Before you randomly to color the complement of A union B, and you find with good probability, with high probability, a set from FB prime in one color and set from FA prime in the other color. And this would correspond to two disjoint sets. And that's the verification of it.
Thank you very much. Yeah, very nice results. So this time, combinatorics beats algebra.
Yeah.
Any questions or comments?
Yeah, maybe I should add that it's work in progress, as I said, but I really hope that in the next month we'll have something out. It has been lying for too long. I thought about it more than half a year ago and still haven't written anything. I mean, we wrote things, we haven't put out anything, but yeah. Many things are written. Well, the things that I told you are written down, but still kind of hesitating. There are many other applications. I don't know what to include, what not to include. It's, there are many directions to go, kind of.
What about the upper bound for T, this root n? Can it be, is it best possible, or it can be?
No. It's actually, so for, it's interesting. For Alweiss-Khachaturian, the threshold for the sets, this threshold is around, well, it's n, roughly speaking, or maybe not even roughly speaking, k minus t times t, something like that. So that's the threshold when for bigger n, the extremal configuration is this trivial family, all sets containing fixed t. For smaller n, you need something else. You need this A1 that I was defining in another family. So that's for sets, T intersecting. For permutations, it should be something like n equals 2t. So t should be n over 2. Somehow permutations are, except for the fact that they're very sparse in the amount of in the sets, they are in ways easier to deal with. And in particular, this threshold, I think it's 2t, if I'm not mistaken. Basically, you just have to compare the trivial family, so this n minus t factorial, versus the family that would fix at least t plus 2 coordinates from t plus 1 coordinates from fixed t plus 2 coordinates. And I think this the other configuration beats it at 2t. And I haven't given it much thought yet, but yeah, that's what I would say at this moment. This should be the threshold. So, and we have some hope that we can actually, that's another thing that we're trying to do now, is maybe to push this result, where is it? This thing, and replace the 0.5 with 1, so make t almost linear. So we have some hope that it's possible. But yeah, unclear at the moment.
Thanks. All right, any other questions? So it seems like everyone is tired because it's late. But it was clear and interesting. Thank you very much.
Thanks a lot.
Yeah, thanks everyone for joining. See you next Thursday.
Thank you, Andrey.
Yeah, thanks a lot, and thanks for coming. Bye-bye, everybody.
Bye.